Now let's talk about how stars evolve, stellar evolution. This is the work that started to be done at the Harvard College Observatory when people saw the spectroscopic properties of the stars, deduced what they were made of, and when we had a quantum theory of matter that told us what the energy source really was. The physicists that took over these calculations were dominant figures in the history of modern science, in particular George Gamow, a Russian emigre, a physicist, also a popularizer who wrote the Mr. Tompkins books, which imagined what it would be like if humans could live and see quantum scale phenomena in their everyday lives. He defected to the United States at the 1933 Solvay conference in Brussels. He was the first to apply quantum mechanics to a nuclear system, and he worked out the first viable mass model that would lead to fusion in a star. As we'll see later, he also coined the term Big Bang and proposed how the early universe could have created the light elements. Another giant in the history of physics is Hans Bethe. He studied in Munich under Sommerfeld, one of the founders of the quantum theory. He emigrated from Germany due to the inhospitable conditions for science as the Nazis came to power, and eventually arrived at Cornell. He was the leader of the theoretical division at Los Alamos during the Manhattan Project that developed the atomic bomb. Chastened by the experience, later he became a major anti-nuclear activist. In 1938, he wrote two pivotal papers, one on the proton chain reactions that operate in the sun, and the other on a new cycle called the carbon-nitrogen-oxygen cycle. He was a brilliant mathematician who deduced quantitative results with what seemed like lightning speed, and they propagated through the field. He was given the Nobel Prize in Physics in 1967. He did important work on supernovae, neutron stars, and solar neutrinos, and was active and publishing frontier work well into his 80s. In 1935, Gamow wrote a paper that outlined the future of nuclear astrophysics. In the animation here, we can see the three-stage process that operates in the sun to turn hydrogen into helium. There's an electrical force barrier between the positively charged nuclei called the Coulomb barrier, and he was the one to work out the theory of how it works. As we've seen, it only works because quantum tunneling allows the protons to overcome this strong electrical repulsion. In low-mass stars like the Sun, a three-stage process operates, where two protons combine to form deuterium with the release of a positron and an electron neutrino. Then another proton is added to the deuterium to make helium-3, an isotope of helium, with the release of a photon, high-energy photon, gamma ray. And then two deuterium nuclei fuse to form a hydrogen nucleus with the release of a neutron. So helium-4 is formed in a three-stage process with the release of energy and other neutrons to participate in other reactions. And so this is a self-sustaining reaction. The Sun and every other star like it are on the main sequence, getting energy this way. And the total main sequence lifetime for the Sun is 10 billion years. Here's the HR diagram so we can see it clearly. Luminosity increasing upwards to the most luminous short-lived stars and downwards to the lowest luminosity dwarf stars. The diagonal band is the main sequence, and you can see the Sun at the middle of the main sequence as a moderate temperature yellow star at its surface. The very massive stars at the top end of the diagram in the top left are actually very rare, whereas the low-mass stars on the bottom right are quite common. The question might arise, why can't there be stars of any mass? Why couldn't there be stars 1,000 times the mass of the Sun, or 10,000? And the reason there is simple. As we now know with computer simulations, a gas cloud that's very massive, 1,000 times the mass of the Sun, or 500 or 5,000, can definitely collapse by gravity, but it collapses so violently that it blows itself apart before stabilizing as a star. So nature's put a natural limit of about 100 times the mass of the Sun on stable stars forming. We've not really found stars much more massive than that. At the low end, what forms the boundary to stars? There are many gas clouds of low mass that could collapse to form clouds that are 5% or 1% or 0.5% of the mass of the Sun. What happens there? Well, those gas clouds will collapse and be held together by gravity, but the temperatures at their centers will never get to the point of having nuclear reactions. The low threshold for the first nuclear reaction to make deuterium is about 2 million Kelvin. The sun's core temperature is more like 15 million for a full-scale process that creates helium. So there are plenty of gas clouds around that are collapsed by gravity but are just too cool for nuclear reactions, and so they're not stars. They're not shining by their own light. Let's see how stars are cooked up.
Welcome back to the Star Cook.
Thank you, thank you. Welcome back. I'm Michaela, and I'm here with my very special guest, Mr. Bill Nye.
Thank you, everyone. Michaela, it's so good to be back on the show, and you are looking fabulous.
Thank you. You too, you too.
Oh, thank you, Michaela.
So tell me, Bill, what are we going to do today?
We have here the ingredients to make virtually anything.
Oh, these are different kinds of atoms.
That's right. These are all the different elements, all the different kinds of atoms in the universe. Now, atoms come from stars. Now, take, for example, our planet. Our planet has a lot of iron and silicon, along with many other elements. And our star has a lot of hydrogen and helium. Now, Michael, oh, that's our hydrogen. Almost lost it there. It's okay, everybody, it's okay. Now, Michaela, you and I are 65% water.
Right.
Now, what's water?
H2O.
That's right, H2O. I have some water here, which I prepared earlier.
Well, of course.
And the water is 2 parts H and 1 part O. H2O, water.
So with this here, we can make virtually anything.
Well, actually, no. Because in order to make all these atoms, you need the force of exploding stars and billions of years. But brownies, on the other hand, only take about 35 minutes.
And even brownies are made of atoms.
That's right.
Oh, Bill, this looks fabulous. People, it looks fabulous, doesn't it?
Oh, thank you. Here, Michael, you please have the first one.
Oh, thank you. Oh, delicious. We'll be right back.
Thank you.
So let's look at how heavier elements than helium are made. And this requires low-mass stars, but a little more massive than the sun. Helium fusion requires a higher temperature than hydrogen because the larger positive charge of a helium nucleus with 2 protons means that it's harder for 2 helium nuclei to fuse. There's another important detail about this process because the fusion of 2 helium nuclei, building it in stages, does not work since beryllium decays in a tiny fraction of a second, less than a trillionth of a second. And so as soon as 2 helium nuclei fuse, the decay product disappears. So helium fusion has to operate by combining 3 helium nuclei simultaneously to make carbon in one step. And that's less likely. The triple collision is rare, and so carbon is hundreds of times less abundant than helium. And that explains one of the drop-offs in the abundance of the periodic table chart that we started with. In fact, it's a fluke that carbon can be made at all, and just as well for us, since chemistry and biology depend on making carbon. And carbon, as we know, is a girl's best friend.
A lithium dose just might cure your depression, but carbon is a girl's best friend. And gold may be grand, but it won't start a fire in your barbecue or put the toot in your choo-choo, 'cause life on Earth is carbon-based. It came here on rocks from outer space and formed organic compounds till the carbon cycle went round and round. Carbon is a girl's best friend. Well, there may come a time when you need to do some squeezing. Carbon is the world's hardest friend. if you have some lube and to do, then graphite is the allotrope for you. Or if you're into ages, then carbon-14 can date it. Carbon is a girl's best friend. Well, I've heard of attempts to make hard carbon nitrides, but diamonds always win in the end. You know they do, darling. And I've heard that we need to find something much cleaner to put into our cars, or else we won't get very far, 'cause time rolls on and supplies will be gone of diamonds, coal and petroleum. But nanotechnology can build anything with fullerenes. Carbon! Carbon, yeah! I don't mean hydrogen, but carbon is a girl's best friend. Best friend.
Let's look at how the high-mass stars make even heavier elements. We can think of this like Legos being put together in the atomic nuclei. Helium capture reactions will add 2 protons at a time. Remember that helium has 2 protons and 2 neutrons, so it boosts the atomic number by 2. Advanced nuclear fusion reactions require extremely high temperatures because the positive charge in the nuclei is increasing, so their electrical repulsion and resistance to fusion is increasing. And eventually it requires billions of degrees Kelvin to create the heaviest nuclei of iron. You can see in the diagrams here how that fusion chain goes up, and in the animation you can see how the helium nuclei are added sequentially. So only the highest mass stars with the largest amount of gravity can ever attain a high enough core temperature to create the elements up to iron. In other words, heavier and heavier elements are created sequentially by more and more massive stars, and the low mass stars, like our Sun for example, will never be able to do more than make a little bit of carbon, and it will stop there. Even the most massive stars stop with iron, however, because it's the most stable element. In the advanced stages of nuclear fusion of a massive star, the fusion is occurring simultaneously in multiple shells at different temperatures, with the hotter layers near the core creating the heavier elements in a sort of onion skin model that we see here. Now this is a cartoon version. Of course the plasma is in violent motion and there's turbulence, so there's a lot of mixing between these layers. Meanwhile, this is a process that cannot continue up the periodic table. Iron is a dead end for fusion because nuclear reactions using iron do not release energy. In other words, energy has to be added to go beyond iron. And we see this in terms of the stability chart of the atomic table, where energy is released by fusion going towards iron, but fission releases energy coming down from heavier elements, and that's why we have radioactive decay of the heavy elements towards iron. Iron's the most stable element, and so something special has to happen to get us beyond iron in this process. We also see in this diagram the evidence for helium capture, the sawtooth pattern. The higher abundance of elements with even numbers of protons, that sawtooth, is caused because there's always hydrogen available to add 1 to an atomic number. That moves the curve up uniformly. But there's also a fairly large amount, 1 part in 10 per number of atoms, of a helium nucleus, which adds 2 protons and increases the atomic number by 2. So there's an enhancement of even atomic numbers over odd atomic numbers. We see the secondary peak at iron, the most stable element, and the heavier elements, much less abundant than iron, are produced in supernova explosions and in very rare neutron star collisions. And so, at this point, we have explained the major features of the cosmic element abundance. Hydrogen is fundamental, and helium was actually fused in the early hot Big Bang, a separate topic. The elements from carbon to iron were fused in moderately massive stars in sequential fusion stages that involved more massive stars to create the heavier elements. The elements beyond iron, where there's a pileup and energy has to be added, that energy must come from supernova explosions and neutron star collisions, and that explains the extreme scarcity of elements beyond iron. And the sawtooth is helium nucleus being added, with the trough due to unstable atoms that disintegrate before further fusion can occur. It's an amazing intellectual achievement for astronomers through the 20th century to have explained this aspect of the natural universe, the abundance of the periodic table out there in space throughout the universe. We tend to think of stars as light bulbs in the sky, just emitting energy, but that's actually the wrong way to think of them. We should really think of them as chemical factories. It's as if there was a factory making things and some light was leaking out, and that's how we knew the factory was there. The leakage of light from stars by a residual of E equals mc squared by less than 1% is really the light leakage from a chemical factory, from a factory that's making heavy elements. Since some of these elements are essential for life, in a way we can say that the universe is built for life. And in modern astrophysics, we've now pieced together this view of where the elements in the periodic table come from. And you can see a variety of sources. The light elements at the top from the Big Bang, the massive stars, the middle part of the periodic table, and then the dying phases of low mass stars, the middle part of the periodic table, but also exploding white dwarfs, cosmic ray fission. There's a variety of mechanisms now, and we're still learning about these processes in different stellar sources. And that's the end of this topic.